Thank you everyone for attending this talk about verifying Peephole rewriting in SSA compiler IRs. So I'm particularly pleased to give a presentation here because I kind of don't self-identify as a formal verification person. And so I had the challenge that I was quite nervous to kind of give a talk to you about something that I'm potentially eventually become. But let me motivate a little bit where I actually come from. And so kind of starting from my PhD over almost 10 years, I worked on polyhedral loop optimization. So there's some mathematics in the 1960s about polyhedra. You recognize that they're really good in modeling loop nests, and then there was an early implementation of kind of constraint-based loop optimization in the 2000s. And kind of when I started to be an undergraduate student, it's actually a funny story. So I was 2 years into my bachelor's degree, and I found this little project list on a professor's door with many student projects. At the very end, there was this project was called Bring Polyhedral Compilation into Real-World Compilers. And I thought 2 weeks into my bachelor, this is the right project for me to get started. So I started to develop Graphite, which is a polyhedral loop optimization framework in GCC. That's how I learned C programming. A little bit later, I developed Poly, which is an polyhedral optimizer for LVM. And then kind of AI happened, and a lot of these things kind of moved into DSL compilers for deep learning. So one of the interesting takeaways that actually I, as a young student at that point, took me a lot longer to realize is our math library that we developed for our constraint programming actually was built on a tool called Simplify. In fact, it wasn't built on that tool, but we used the same kind of simplex solving strategies to do our constraint programming. So some of what I guess most of you use in SMT solvers, we use the very same technology for a slightly different use case. And so over the last years, we went a little bit crazy and built a full-scale Pressbooker solver into the LVM project and in particular the MLIR project. Yes?
What is an LP solver?
Linear programming. So linear programming, not integer linear programming, but kind of our integer library uses a linear programming solvers to identify redundant constraints. And so actually what's quite interesting is the way we use these kind of techniques is slightly different to what a typical SMT solver would do. So we would typically don't solve really large problems. We solve many very, very small ones. And we actually typically don't even want to solve them. We typically just want to simplify kind of the constraint representation and maintain a relatively small constraint representation. So in fact, over the last years, we've published a couple of papers to kind of optimize this particular algorithm for our specific use case. But I'm telling this story because I think it's interesting to know that some kind of formal methods is used in LVM since many, many years. But it's slightly different from the typical SMT solver people would use here. The other thing that I think is a little bit atypical, how do I do my research, is that I actually, as a PhD student, I contributed to LVM. In fact, so this is it was a bit lucky because Chris Ludler said if I want to develop a loop optimizer for LVM. So in fact, almost never in my research career, I actually wrote code that was not committed to a large open source project. Even today, like 80, 90% of my code overall lifetime is probably committed to one of these large projects. And so the same holds for my research group. So we typically present at the LVM dev meeting, and kind of 80, 90% of our code ends up in some kind of open source repository, which I think is quite interesting and gives you a little bit the context where I'm coming from if I want to build software. And so before I go to the formal methods aspects of what I'm building, I want to briefly explain to you kind of what we do on the kind of performance engineering side in LVM, the kind of research we're doing there. And here the objective is to build a static analysis to understand that piece of code or larger variants of that piece of code. So if I ask you what's the computational complexity of that code, I would guess most of you would say that's probably cubic in a way. It's relatively easy, right? But if I ask you these questions, what's the percentage of cache misses of that code?
It depends.
At that point, the answer is relatively simple, right? You need the cache size and the cache line size. But even if you have that as a human, it's close to impossible to guess these values. And I find that interesting. It's relatively easy for us to compute, kind of in our head, the computational complexity of these codes. But cache analysis is a very non-local property. It's very easy to get wrong or even to not understand just because of the complexity of these codes. This is the most expensive memory access if anybody wondered, and this is the count of like compulsory and capacity misses in this code, right? And so compilers are typically not particularly good in non-local reasoning. They're quite good in kind of fiddling a little bit with the code and making it better, but really understanding what's the right tiling strategy, these kind of things. Compilers typically didn't have a good cost model. So one of the recent challenges that we worked on over the last 3 or 4 years was to build cost models that scale to such kind of programs. In fact, we started with like relatively small kernels. We realized if you optimize them, they actually become a little bit larger. And then we realized that actually a full deep neural network is actually where you want to understand the cost of or the memory behavior of these things, right? That's what all the like deep learning compilers, they try to optimize these networks, for example, for minimizing cache misses. Yes?
Comment on the trade-off, maybe of the relationship between trying to make some analysis to figure out these costs versus running it a few times and instrumenting it.
Exactly. So maybe wait 2 slides and then I comment on this. So one of the main questions really is you have 2 kernels and you may want to fuse these loops, right? It's one of the very basic questions a compiler might ask. Or what's the tile size of these loops? How do you want to implement them? And for that, you need a precise answer. What's the computational cost? And as Peter said, we can execute them, right? So in theory, we profile that thing. It takes 20 minutes. We take a coffee, and then our compiler has, for like a single data point, really good understanding how fast that thing is. If we want to do search space exploration, we need a lot of coffee breaks or just a lot of machines to explore these things, right? And so one of the interesting things about kind of strong static analysis methods is that you can be faster. So the tool that we built takes 12 seconds to pretty much give you the same answer. Not exactly the same answer. It's a simplified cache model. There's a certain noise compared to the actual hardware. But interestingly, it's deterministic, which makes it for certain search space exploration challenges or questions. Actually a better tool because it's more deterministic. So what's the key idea? There's an entire paper around how to do that. I skip over this because the entire point of this part of the presentation really was to motivate a little bit that we actually have quite powerful static analysis in compilers meanwhile. But there's a very nice, cute mathematical tool that we used that I think is worth sharing. And so the kind of tool that we use there is we reason a lot about sets of points described by linear inequalities, or we call them Pressburger sets because we are slightly more generic than linear inequalities. And one of the key tools we need there is counting these volumes. So you have a polyhedra where you have integer points in that polyhedra, and you want to understand how many points are there. And particularly, you want to sometimes do that parametrically. So you have a cube of like n sizes on all sides. You want to know what's the volume, right? And so a simple way to do that is to just count the points, right? You start at I, you go to j, so you go I plus 1, I plus 2, so you have 3 points. That is a relatively easy way to count, but obviously that is slow, right? Because you actually explicitly reason about each individual point. A different way to count is symbolic counting. So here you just take the upper bound, subtract the lower bound, you add 1. That is asymptotically faster for a 1D problem, right? And interestingly, obviously if the interval becomes larger, these asymptotics are beneficial for you. I don't talk about how we do that, but there's a really cool algorithm of Alexander Babinok, which can do that for arbitrary shaped polyhedra with arbitrary dimensionality, which just gives you a closed form expression of the number of integer points in that volume. And that's the way how you kind of, instead of simulating, as you suggested, Peter, you build relatively complicated constraint systems, many of them, and at some point, in fact, twice, you count. And if you're eventually the number of cache or the reuse distance of your memory access is larger than the cache size, then you have a miss. If the reuse distance is smaller than the cache size, then you have a hit. Right? And that's a little bit kind of a small story about why, like a compiler person as I am, would actually build quite sophisticated static analysis to get an understanding of how programs behave. Okay? So, just a couple of figures. There was previous work which worked on like kind of microkernels. And this very recent PLDI paper, we expanded this to full deep neural networks, so they are a lot larger. Our tool is a lot faster. So instead of hours for the old one, we are like in a couple of minutes. And so the takeaway is that actually formal tools exist in compilers. In fact, we develop constrained programming libraries in compilers that are by far not trivial. And we can scale to relatively large problems. Yes?
But the name of the game here is basically to try to figure out some kind of magic number to figure out if you should perform a transformation.
Exactly, yeah.
So the worst thing that can happen here, if the answer of your formal method is wrong, that you actually make your code slower.
Yes and no.
Can you actually the wrong result here actually result in your compiler being unsound?
So in fact, I like a lot of the loop transformations that I built actually transformed the code. So they use both the formal method as a cost model, but also to decide on code transformations. In particular, like how to rewrite transform like expressions, which sub-expression you can eliminate. So sometimes we identify like sub-expressions that are implied through like earlier constraints. And so for any of these kind of rewrites, yes, we can make that thing particularly unsound.
Oh, okay. So these analyses, they do both. They determine whether you can rewrite something at all and the cost at the same time.
So I mean, I just presented like one of the recent parts of our research, but I mean, I worked on that for 10 years. So we use a lot of the technology for like major rewrites and analysis of code. So yeah, we can definitely be broken. And in fact, I guess that is one of the 2 papers in my life that I have written and not published. One of them is trying to prove our analysis correct and having seriously failed. This is, yeah, if you want to have a really difficult paper to write, that's one. Yes?
Fail to publish or fail to prove correct?
Well, like failed step number 1. The proof didn't even go through. So and that is actually quite a good question, like why am I here, right? So I got bugged a little bit. I didn't like that I didn't get the proof through. It was also not perfectly scoped. I think we could have proved a slightly simpler variant of whatever we actually implemented in practice. But yeah, it's quite annoying, right? So what do you do when you get quite annoyed? So I personally kind of hook on some problem and try to fix it. So that's why I'm here. And so we have a lot of these formal tools in the compilers, but we had amazing talks earlier about like formal semantics for x86, for example. Obviously, what I presented right now is nowhere close to that, right? So the question is, can we get that, right? And so talking about large projects, Linux has 1.3 million commits, not lines of code. Chrome has around 1.4 million commits. LVM has, just a second, has 500,000 commits since the project started.
So just to make sure I'm following, you want specification for LLVM or for the cost model of CPUs? Or?
So this is kind of like a task jump switch, right? I thought I have a problem with my analysis, so maybe slightly overambitious. I think I have a problem with LVM. So I want to eventually get more formal verification into the LVM ecosystem. Obviously, people did that already, right? We had talks about ComCert. Verifying compilers is incredibly hard. So first of all, I'm maybe not the expert to do that. And second, it was already done, right? And ComCert is an amazing tool, right? So it's 100% certified. You can trust it. It's used in planes. It's pretty much gold standard of where you can get. I didn't work on ComCert, but I heard it's painful at times. I'm not sure what the ComCert developers say, but that's my impression from kind of an LVM developer perspective. The kind of complexity and of reasoning versus like building LVM, I think might be slightly more complex. And the other thing is it's a little bit of a disjoint development, right? There's clearly like there's a ComCert community which do amazing work on the theory side and on the formal side, and there are the LVM people like me who kind of just built their buggy compiler. but it's also like the speed of kind of, I'm not sure if I picked the right repository, but I think there's roughly an order of magnitude or even more in terms of commits per day, right? So the LVM project is evolving quite fast. And so there are efforts to verify LVM. VLVM is one of them. But a lot of these verification projects, they need to play catch up, right? I guess some of you have verified real world things. And typically, I would guess you play catch up with like really motivated engineers that are typically have more resources, more people to build more powerful things. And then we need to kind of play catch up. So my question is, how can we solve that problem, right? I don't think I'll ever build something like ComSort. I think it's quite difficult. But my ambition is scale. I want to validate something in LVM. And yeah, how can I do that without playing catch up? And so one interesting insight from ComSort is that ComSort has kind of showed that like multiple levels of abstraction in a certified system are actually really helpful, right? And it did that 10 years ago before at least the LVM community figured out that this is an interesting thing to do. LVM historically was a classical compiler with a one IR. And over the years, there was Swift that used LVM, and they figured out one higher level abstraction is actually quite useful. The Rust people realized two high level abstractions are actually quite useful. Many domain-specific compilers added a couple of more abstractions. And so overall, the LVM ecosystem, meanwhile, involves an entire DAG of abstractions that you can mix and then combine together. And this projection of this DAG is one specific deep learning compiler that translates over different abstractions to generate code. Right? And so interestingly, kind of 10 years after ComSort suggested this, the MLI community or the LVM community realized that having many abstractions is not only useful for formal verification, but in fact it's really useful for optimizing or adding domain-specific optimization into your compiler stack. So in that setting, the LVM community is playing catch-up. It took us a couple of years, but we're getting there. And so now let's think about, like, did we actually, yes?
So are you saying LLVM is sort of migrating towards using MLIR as a central, or the different instantiations of the different languages modeled in MLIR as a sort of...
So I mean, there's a difference between LVM as a project and LVM, the specific code base of the compiler. So there's an LVM compiler which has load, store, arithmetic as its IR, and then backends. But there's the LVM ecosystem where there are many more higher level abstractions. So for example, the Fortran compiler has now a higher level Fortran abstraction. All of the deep learning compilers have linear algebra abstractions. There's a like fully homomorphic encryption community which has abstractions for these things. And so
Clang is still very traditional, or do you expect it to also go that way?
So Clang has a CIR that is a lot higher level. That's currently developed by, I think, Meta. So I think the actual C++ part of the community is moving a little bit slower. But I think there's a clear trend that a lot of high performance stuff is developed in the MLIR space. And the main reason is if you want to use your scalable matrix extension on your M4 that you buy 1st of November, actually recovering the matrix operation on LVMIR is so much more complicated than just having an explicit representation of that thing in your higher level abstraction, right? So yeah, I think it's almost unavoidable that even LVM, but certainly the entire ecosystem moves towards that direction. And now let's look a little bit about, is there actually already formal verification in the LVM ecosystem? Maybe the problem is already solved in parts, right? So this is Asterix, this little village somewhere in France, which maybe has already solved that. And yeah, one evidence is we are moving towards multiple abstractions. You could see that it's not verification, but it's moving towards a representation that I think is more amenable to verification. The second thing is not in LVM, but coincidentally in the lean ecosystem, there's an incredibly large formal verification effort for mathematics, which if you reason about matrices, for example, there's just a theory that you could pair up with the abstractions that the LVM ecosystem is building. And lastly, by the way, this is kind of a picture of the math ecosystem, what's mechanized and formalized. But it's actually similar in kind of like the size of that ecosystem. It's a large-scale open source community that builds kind of an integrated ecosystem about stuff that might be useful for us as a community. And the last thing is what we had on last Monday as the opening talk, I think, of this workshop, not this week, the week before, from Nuno Lopez. There's a tool called Alive, which was published at PLDA 15 by Nuno, David, Santosh, and John Reger, which is a tool called Alive, which if you're an LVM developer, you might see it every 3 to 4 days in your commit logs, where some developer is too, I guess, busy with life and family to really have energy for a 2 or 3 day discussion about the correctness of certain bit fiddling stuff. And so they just copy a link to Alive, which is an online tool which just tells everyone who's interested that this commit is correct. And there are, like, meanwhile, 4,000 of these commits in LVM. There's formal semantics pretty much used day to day in the LVM ecosystem. Yes?
So you've gotten a little philosophical here in a sense. I mean, you're trying to, I guess you're saying that maybe that formal methods for LLVM and some of these other tools is good, and you're trying to get us to use it. What do you think you're trying to do here?
I mean, I guess the point is I'm interested in using formal methods at scale to verify not all of LVM, but a subset that you can automate enough to verify.
So it's specific to LLVM, your wishes.
The LVM ecosystem, let's say. That's my home. That's what I know. That's where I think there's something I could contribute to. Yes.
Okay. Yeah. I was just going to say there have been other projects, prior to this one, and one's discussed here, and we've all wanted this at one time or another in our careers. And I think back to the computational logic stack of the 90s.
Yeah.
Where there was, verified hardware, verified assembler, verified compilers, multiple ones, and it looked very much like your chart, except it was just old school, and it was all theorem prover based and everything. And so I'm glad to see how much has happened since then.
Yes.
And but you're proselytizing this in a sense.
So I mean, like, one way to say what I'm doing, yes, I think you're completely right. Pretty much I'm looking into the 80s and 90s and like early 2000s, what people wanted to do there. And I think I try to do it again with like probably half the expertise in that area. And so the question is, why would I even propose that, right? Why would that make sense? And I think one of the interesting things is that, for example, the LVM community is actually out of different needs moving to more abstractions. It's not that I'm suggesting them to adopt a ComSat style design, but the community by itself moves towards such a design, right? And so the other thing is, I mean, technology actually has advanced. I mean, you presented a lot of like really powerful technology. I think might be a good time to kind of like, I mean, not prove all of LVM, but maybe prove a little bit more. And obviously, advice across any of these lines. I mean, I enjoy this workshop very much, right? I mean, many of the things I think about, I just listen to people, and I pretty much just need to read all papers, and many of that has been thought about. Yes?
Actually, the citation is wrong already. It's Alive 2, which is different from Alive. And that's a KDA 2021. They have different tools.
Yeah, I know, but...
And then that's Alive 2. Alive 2 is what's used by LLVM. And then actually that's a collaboration between my group and Nuno's group.
Right. So
yeah.
so there's an interesting difference between Alive and Alive 2, right? So Alive 2 is a translation validation tool that actually, I mean, this is an example of simple Peephole rewrites, which I think Alive itself already proved.
Oh,
and
so people use Alive and Alive 2 both, you mean?
So the software based used in it, like the software base linked here is certainly Alive 2. The example that I showed is a simple Peephole rewrite, which I think Alive already proved. Alive 2, I think the main contribution was that it can handle a lot larger programs, right? So in some way, this is an understatement. I think the research you did with Nuno actually can cover even larger programs than the ones I showed here.
So,
right?
So Alive is usable now? I mean, I think that what I understand is that alive2.llvm.org has a providing tool.
Yeah.
That tool is developed by my group and then Nuno's group.
Yeah, exactly.
But the citation is not Alive 2.
I should probably cite both, right?
Yeah,
I agree.
but,
I should cite both. I agree.
yeah, okay.
Yeah. I guess the point of, anyway. Yeah.
So just to come back to I think if you're making a call to arms, in some sense, that we should validate LLVM to LLVM transformations in the same way that, let's say, CompCert did and other efforts, then I get it. And, you know, like SCL4 and so on.
Yeah.
I mean, that's what you're trying to do, is get us all to, I mean, or get enough of, because then you need a project name and or something. Maybe you got that, but you kind of get where I'm going at.
So, I mean, I'm excited about like looking into that direction. I'm not saying like everybody in this room should follow.
If you organize it and you get a bunch of people behind it, especially if you can get some money for it, like, you know, 50 million or 20 million or whatever, then you can get a bunch of scientists to get in behind you, and maybe we can make LLVM more reliable.
So,
in the same way that CompCert, you like CompCert, now I'm trying to goad you into doing it for LLVM.
all right. I think I need to move on a little bit,
Okay.
but I think this is a really good point. I actually don't have a concrete, I mean, I have a plan what I would like to do, and then, I mean, if there's feedback from people about what is actually the right thing to do, I think that is an amazing conversation to have, right? Let me show you a little bit what I'm doing, kind of my baby steps, and then see if that goes in a direction that anywhere is useful, right? All right, so what we built is actually a tool, we call it Lean MLIR, which is solving the easy problem, or the easiest of the easiest problems, right? So we immediately agreed that we don't want end-to-end proofs. These are really hard. We want to find something that evolves with the semantics of LVM or MLIR at a pace that the community evolves. We want it to be trivial for compiler people to use. It needs to be so low effort that in your day-to-day development, it actually saves you time rather than costs you time. And the only thing we really could think of that's worth optimizing is pretty much looking into Alive and kind of the Alive effort, which was the only evidence of formal methods succeeding in LVM. And see, can we kind of like maybe add an additional level of verification around, and like not even Alive 2, Alive itself, like just the people rewrites verification effort. And so that is the first work that we did. And it's really just optimizing straight line code with people rewrites. In LVM, that's roughly 10% of the code base of LVM itself. It's just a huge collection of rewrites. So we thought if you drop like data flow analysis from that thing, maybe it's only 3 or 5% of the code base that has just rewrites of a bit vectors, relatively simple. We're only aiming for verifying these things. And so LVM has this MLIR project, which is a generalization of that IR for different domains. This has a relatively simple syntax format, and we just express the syntax in this lean interactive theorem prover. Yeah, I'm not sure if we took...
You say it's relatively simple.
Again? So the syntax...
So what does this whole line mean? You say it's relatively simple?
So it's an SSA format, so this is the return value. Each operation has a name in a namespace. It takes a list of operands, and then it has some types, like just syntactic types. It's incredibly, it doesn't even have a, so the entire MLIR project is not even, from a PL perspective, I think it's a little bit shameful. It doesn't have semantics. The only thing it really does is kind of is a pretty printing format of a kind of a structured JSON that allows you to represent SSA-based IRs in a way that is familiar to the LVM community. And then the interpretation of what the semantics mean are kind of partially defined by the rewrites in the community. It's an incredibly noisy, incomplete ecosystem. But kind of the main thing is that then in the end, you can model almost everything that the LVM community can model just by this like having pretty much a sequence of function calls, or like in the function world you would call it let bindings, which happens to have syntax that the LVM community is familiar with. Exactly, so we modeled that, and so I don't think we were particularly experienced with Lean, but we hired one of the math developers, and so we came up with a heavily typed, dependently typed implementation, kind of these core data structures. And what we also did is to kind of make it easier for developers to integrate their code and use our technology, is we kind of embedded the entire LVM syntax through a syntax extension into the Lean theorem prover. So if you feel like using our tool, you just copy paste your LVM code, and then you kind of get a translation into the lean data structures, which I think is quite cool. And we modeled large parts of the MLIR syntax in this like syntax extension, which means I think that at least like makes this kind of transition towards the like more formal world simpler. Yeah, there's a lot of macro rules that were written, and exactly, then you can pretty much model the same thing. You have a before program and after program, and then we have a way to define a Peephole rewrite, which is the left-hand side and the right-hand side, and you have a proof obligation that your proof is correct. Yes?
But don't you have to give some interpretation to add and this and that?
Yes. In 2 slides, I talk a little bit about the interpretation. But kind of the workflow, I think it was important to me to first show the workflow. So you copy your code before, after, using LVM syntax, and then on the right-hand side, we eliminate most of the noise of LVM, and we just get an expression level statement over bit vectors, where you then have a proof obligation, right? And so we have a proof hammer that closes that thing, and now we have that one Peephole rewrite formally proven. So this is lean, like Coq. It's a small proof kernel, slightly smaller than Coq. But that's pretty much the same thing than Alive did, way less than Alive 2. But this is kind of formally proven with a small proof kernel. And at some point, there's a lot more we did, but I think that's actually quite a nice achievement for a compiler developer. This is kind of close as the like feedback loop. Now people can go, copy, paste their code, get it verified, continue with life. Yes?
I mean, technically with MLR, you use it like a dialect, right? When somebody else has provided it, or you've written yourself. So does that mean that a dialect provider also has to then provide all the semantics as well, right?
Exactly. So let me just go a little bit further, because I had the second question already about semantics, right? As a compiler developer, I put them a little bit last, but this is just kind of like a little bit of our type system. So by pretty much declaring an IR, you define types, you give type denotations, you declare operations, you give their signatures, and then you have operational semantics for all of these. That's pretty much how you define a simple constant and add in our framework. So what's interesting is like kind of the entire meta proof that we wrote is generic over the semantics. So kind of the concept of SSA and how that, like the MLIR syntax, that's all kind of meta code or like generic over the semantics, and with a lot of type classes, which again may not have been the best choice, but kind of then you pretty much can instantiate the semantics for a given dialect. Exactly. Then there's a lot of definition. I go a little bit faster because there are a couple of other things I want to talk about, but a lot more lean code around these lines. Then at the end we can have a function rewrite Peephole, which pretty much takes a Peephole rewrite and pretty much says that if we have a target program over which we run our Peephole rewrite, then pretty much does the same thing as just having the target program evaluated without the rewrite being applied. And so this is a small rewrite engine. We have our formally verified rewrites, and we can, if we gather a large collection of them, we can apply Peephole rewrites over our LVM or MLIR project. Yes?
So one of the things with your live project, I don't want to get it wrong, but hopefully I'll get it right, but you actually,
speak up, please?
for the live projects, you actually give the whole translation as a sort of DSL, whereas here you seem to be lifting 2 pieces into lean, so it seems that there's slightly more of a step here to sort of know you're connecting with the correct piece. Is that fair to say?
So, I mean, I think that might be, again, the difference between Alive and Alive 2, right? Alive was pretty much just Peephole rewrites. And Alive 2 is a lot more powerful, right? You have a, pretty much, it's translation validation tool. You run entire pieces of a program, like large-scale pieces, and then prove equivalence there. Like, we don't do any of that. We really do the simple stuff.
I guess I'm just wondering, sort of from software engineering, as the code evolves, how do you ensure people keep updating the lean?
I mean, so for once, actually, I mean, the semantics for like bit vector So we are not looking at like full state semantics with like load and memory and all these kind of things. So in that sense, our semantic surface that we use is a lot smaller. The second thing we are doing, I don't have that in the talk, but so MLI is nice because you can instantiate dialects for arbitrary domains. And so coincidentally, we instantiated a dialect that's called the SMT dialect, which happens to be a semantic dialect in the MLI ecosystem. So it is used currently only in our hardware sub-project to implement a model checker. But the general vision is that kind of the LVM community would maintain their semantics by just translating to the SMT dialect. And then we kind of have an automatic way to kind of extract the current status of their semantics. But yeah, I didn't talk about that too much. It's very much work in progress, very early work in progress. Exactly, so we implemented our rewriter using zippers. Again, looking at the time, don't explain that too much, but pretty much we do a like rewrite at an arbitrary place in our data structure. Have all that formalized. MLI also supports structured control flow, so we have, if you have completely side effect free, we can handle something like an iterator, so iterative loop. Again, only the simple stuff, not very effectful. We have a simplified model of what is called poison in the LVM ecosystem. So Nuno gave a really interesting presentation how you model undefined behavior. I guess you have that also like in a live or live 2. So LVM has this really funny concept of not just undefined behavior, but what's called poison is delayed undefined behavior, which is a kind of useful semantic concept if you want to speculate on certain optimizations. So we modeled that in a slightly simplified way. We tested everything, and it seems that our semantics are for like small bit widths, they are fine. And we built proof automation. I think that's the other thing that I'm quite excited about. So we have kind of, whenever we build something, we have CI that tests this, and then often these tests use our proof automation. In particular, Lean had a bit vector library, which some of the CVC4, 5, and Bitwurzler people started to build, and we kind of expanded that. And then we built a couple of simple or not so simple extensions to that theory. Proofs via extensionality, via ring tactic work. We have an automata tactic for like some kind of Pressburger logic. And if we happen to have fixed bit width, then all of them can be proved by something that's called BV-decide, which is a bit blasting SMT solver for the bit vector theory. So BV-decide particularly was co-developed with the Lean FAO. So Henrik was the lead developer here, but many other people kind of helped us build this bit vector theory in Lean. We have the full SMT-lib bit vector API surface, and kind of this is just a table of a couple of like cross-cutting functions that have been implemented or verified and not yet. And BV-decide is what I think is actually, maybe that's another slide where it's worth to go a little bit slow. This is a fully verified re-implementation of the Bitwurzler bit blaster. Bitwurzler won the SMT comp, I think, 2 years ago. What's verified is the kind of the rewriting on the symbolic level, the canonicalizing to a small subset of SMT-lib API surface, the translation to the end inverter graph, translation to the SAT proof, then there's an external SAT solver caticle plus a formally certified checker, and then they communicate using this LRAD format. We have a couple of division circuits, multiplication circuits, all of that is formally verified. So whenever you use BV-decide for fixed bit width, it's pretty much like you have a bit vector level theory solver that can solve that problem for you. It's only 2 days ago that Henrik posted that we added division support, and so for one specific crypto example, we are faster than C3 and CVC5 by quite a bit. Bitwurzler takes 22 seconds for this specific example. I think we take, depending how you measure, between 33 seconds and 24 seconds. So that obviously, I mean, this is very much research work in progress. That's not a performance evaluation. It's a very simple single data point. Not sure if you want to take any conclusions from that. But I mean, the main thing is the bit blaster works. It's proven, so I hope it's relatively bug-free. and it's at least for that one test case, it's quite fast. One small example, just to mention it, we also verified a really, really small subset of a fully homomorphic encryption abstraction. The only reason I showed this that pretty much at that level you can pull in the full power of MATLAB. So the semantic domain you reason about are kind of quotient polynomials, and so they are all nicely defined in MATLAB, so you can just pull them in and use them to define our semantics. And there's a Google framework implementing this fully homomorphic encryption compiler. It's called HARE, so it's a nice project to check out. Exactly, these are kind of our implementations where we pretty much just directly map to MATLAB. And that's non-computable. Couple of extra goodies. We have common sub-expression elimination and dead code elimination for our limited subset of this MLIR. Proven as a meta-theoretic statement. And we have kind of a really simplistic model of some kind of just the fact that there might be a side effect without any kind of semantic power behind that. So no side effect reasoning, no loads, no nothing. So that's pretty much it on the verification side. I have 1 minute, so I have a couple of slides just to point something out to make the connection that we are really just redoing whatever was done 20 years ago. Hardware verification is something that the MLI community also happens to do since 2 or 3 years. This was a PLDI 20 paper that we wrote. It would be useful to use something like LLVM for hardware verification. So then this thing went a little bit out of control, but kind of the main story is pretty much the same. Verilog is the language of hardware verification. There are a couple of high-level languages that translate to Verilog, but in the end there's a large proprietary stack here. Would be so nice if that's not proprietary anymore, but if you would have an LLVM-style open source ecosystem, which we proposed at PLDI kind of in a relatively ad hoc way. Meanwhile, that exists as a kind of project of the LLVM community. Just as a feeling, if you have a little bit of Verilog here on the top, you can pretty much just run classical LLVM or MLIR passes on this to simplify the Verilog code, moving it from a behavioral IR to a structural IR that you eventually can synthesize. And so some of our proofs translate here, especially kind of bit vector reasoning over the computational logic. That's circuit, and there's a web interface for our tool. Thank you.
There are already questions and only 30 minutes left, but if you have one comment or a question? Yes?
So you admire the fact that Alive 2 is appearing in the submission logs. So is what you're hoping for with lean MLI that the reference that in the submission logs for LLVM or commit logs, people put links to lean MLI proofs of the changes that they're making?
Something along these lines. And maybe it's just Alive, kind of we merge more with Alive. So actually Nuno and many people of the Alive team tried to use lean at some point, and there's even a paper around that. Lean at that point didn't have a strong bit vector theory. So I guess one of the where I think was quite stubborn and insisting was to really for a year and a half kind of try to get a canonical bit vector theory into the lean community, which exists now, which is I think one of the things that would enable Alive to build something as Alive, but maybe so lean is developed by Leo, who developed C3 or started C3. So I guess another takeaway is that I think lean is now starting to build SMT automation at a level that is maybe slightly below what is useful for Alive yet. That's why we're limited quite a bit. But one of my students has just put up a patch for accommodation to support that in the lean's decision procedures. So things are getting there, and so my feeling is I don't think I can do that anywhere alone, and I think especially the Alive people are pretty much the highest respected formal verification people in the LLVM community. So yeah, I think if I can contribute in some way, I would love that.
Thank you very much.